Welcome back, listeners, to The Deep Dive, where we plunge into the cutting edge of artificial intelligence. Today, we're inviting you to step inside the incredibly complex world of real-world decision-making. Imagine for a moment a self-driving car navigating a bustling, unpredictable city intersection.
Hmm.
Or maybe a doctor meticulously selecting the best, most personalized course of treatment for a patient grappling with a unique condition. In these high-stakes scenarios, what if critical information vital to making the absolute best decision, isn't directly observable?
Yeah.
What if there are hidden factors, unseen variables, quietly shaping outcomes without us even realizing they're at play?
Yeah, it's more than just a theoretical puzzle. It's a foundational challenge in modern AI, really. Traditional models often operate under the assumption of a complete picture, a perfectly clear window into the environment.
Right.
But reality, as we know, is rarely that neat. It's often messy, full of subtle nuances and unmeasured variables that can profoundly impact the effectiveness or indeed the safety of any strategy an AI attempts to learn.
And that's precisely why today we're taking a deep dive into some truly groundbreaking research. We're unpacking a seminal paper titled Reinforcement Learning with Continuous Actions Under Unmeasured Confounding. This work tackles a crucial, often overlooked problem in the field. How do we learn truly optimal strategies from vast data sets when those important influencing factors are stubbornly hidden? And to add another layer of complexity, the actions being taken aren't just simple, discrete choices, but fluid, continuous movements or adjustments.
So our mission for you today is to decode the ingenious technical solutions proposed in this paper. We'll explore the underlying problems these researchers are grappling with, the novel, elegant methods they've developed to overcome them, and the far-reaching implications for building more robust, more reliable, and ultimately more effective AI systems.
Yeah, we'll be focusing squarely on these technical innovations and their practical consequences, exploring what makes this approach unique and why it represents such a significant leap forward in making AI genuinely reliable in those complex, real-world scenarios where unmeasured confounders are an exception, but, well, a persistent reality.
Exactly.
To that end, let's kick off our deep dive with part one, the invisible problem: why hidden factors confound AI decisions. We've seen an explosion of interest recently in what's known as offline reinforcement learning, or offline RL. Now, we know our listeners are pretty well versed in the basics of RL, but can you quickly remind us why this offline variant is such a game changer? Why is it getting so much attention right now?
Absolutely. So the traditional approach to reinforcement learning, often called online RL, involves an AI agent interacting directly and continuously with its environment. It learns through active trial and error.
Right, like learning by doing.
Exactly. Think of it like a child learning to ride a bike. They fall, they get back up, they adjust their balance, they keep practicing until they get it right. It's an iterative, hands-on learning process. However, in many real-world applications, this trial and error approach isn't just inefficient, it's often too risky, prohibitively costly, or simply too time-consuming to be practical.
Right. You definitely don't want an autonomous vehicle learning from actual crashes on a busy highway, or a medical AI trying out experimental, potentially harmful treatments on real patients in a live clinic.
Yeah.
Yeah.
Precisely. Those are scenarios where trial and error can have catastrophic consequences. And that's where offline RL steps in, offering a profound advantage. Instead of requiring those constant, risky, or expensive real-world interactions, offline RL is all about learning optimal strategies from pre-collected data sets.
Ah, okay, so data that already exists.
Exactly. Imagine having a vast archive of recorded driving data from millions of miles, or comprehensive historical patient treatment records spanning decades. Offline RL allows us to extract optimal decision-making policies from this existing static data without needing any new, potentially dangerous environment interactions.
Hmm.
The paper highlights this perfectly with examples like autonomous driving, where it sidesteps the need for incredibly expensive and dangerous real-world crashes or the immense simulation time required for online learning.
Save a lot of time and money, presumably, and risk.
And risk, absolutely. In precision medicine, it enables safely optimizing treatment strategies by analyzing past patient responses without directly experimenting on patients in risky phases. It's truly a game changer for deploying RL in highly sensitive and critical domains, making it practical where it once wasn't.
So it really opens the door for RL to be deployed in applications where safety and cost are paramount. But this elegant solution quickly hits a wall when we encounter the core problem this paper addresses: the unmeasured confounder, challenge a silent saboteur, as they aptly put it. What exactly is this silent saboteur, and why does it pose such a profound problem for current offline RL methods?
Well, most existing offline RL methods operate under a critical yet frequently violated assumption that all relevant state variables are fully observed. They assume they have a complete, unobstructed picture of the environment at any given time.
That everything that matters is in the data.
Precisely, that every piece of information that truly matters is accounted for in their data set.
But of course, in the sprawling complexity of the real world, that assumption is almost never truly met, is it? There's always some subtle influence, some critical piece of context we don't or simply can't measure.
Exactly. It's like trying to solve a mystery when half the clues are invisible. And what's particularly insidious about this assumption is that it's often unverifiable with offline data. You can't just scan the data you have and confirm that nothing important is missing because, well, by definition, if it's unmeasured, it's not in the data set to begin with.
You don't know what you don't know.
You don't know what you don't know. Exactly. The paper provides some excellent, vivid illustrations. Consider personalized medicine. A patient's unique genetic factors or their deeply ingrained lifestyle habits might profoundly influence how they respond to a particular treatment.
Things you just wouldn't capture in a standard medical record, perhaps.
Often, yes. These are often unseen or unrecorded by the AI making the treatment decision, yet their impact can be incredibly strong, far outweighing the observed factors. Or in robotics path planning, subtle environmental cues, like imperceptible variations in surface friction, tiny air currents, or even the precise historical wear and tear on a robot's joints.
Tiny things.
Tiny things, hidden but absolutely crucial for precise and reliable navigation.
So if these unmeasured confounders are lurking, silently influencing outcomes, and our model doesn't account for them, how do they actually break traditional RL models? Is it like the AI builds a house on a shaky foundation, or does it actively lead it astray? Can you walk us through maybe a scenario where a traditional model truly breaks because of this?
It's a bit of both, really. The AI develops a distorted understanding of cause and effect. Imagine a traditional RL model observing that a certain drug dosage was followed by a positive patient outcome in the historical data.
Okay, looks good on paper.
Looks good. But without knowing about an unmeasured genetic predisposition that actually caused that positive outcome, a genetic factor that made the drug uniquely effective for that specific patient, the AI might mistakenly attribute the success solely to the drug dosage.
So it learns the wrong lesson.
It learns the wrong causal relationship. It's like attributing a lucky break to skill, then trying to replicate that skill without realizing the underlying luck was the key factor.
Got it.
So when that AI then tries to apply this optimal dosage to a new patient without that unmeasured genetic factor, the outcome could be ineffective, or worse, potentially harmful. The model is operating with an incomplete and misleading picture.
It leads to biased, suboptimal, or even dangerous decisions when deployed in the real world because it just can't generalize correctly.
Exactly. It fundamentally misunderstood the true drivers of success in the training data.
That makes perfect chilling sense. To formally model these scenarios where some state variables are unobserved, the paper introduces the partially observable Markov decision process, or POMDP, framework. Can you walk us through that and why it's the right mathematical language for this problem?
Sure. So in a standard Markov decision process, an MDP, the agent has full knowledge of the current state of the environment. Everything relevant is visible.
The ideal world.
The ideal world, yes. But a POMDP acknowledges that reality is often far more nuanced and opaque. Here, the true, complete state of the system, which we can call S, is partly hidden. Only a portion of it, O, for observed state, is directly accessible to the agent.
Okay.
But the true underlying dynamics of the system, how the environment changes, and what rewards are received, depend on the full state S, which includes both the observed O and the unobserved parts. It's a formal way to represent that critical, incomplete picture.
So it's a framework that embraces uncertainty rather than pretending it doesn't exist. And the paper focuses on an infinite horizon setting. What does that mean exactly? That the goal isn't just about maximizing immediate rewards, but the total accumulated rewards over an indefinite future.
That's right. It adds another substantial layer of complexity. Maximizing immediate reward is one thing. You just need to consider the next step. But planning for the long term, especially when parts of the system state are perpetually hidden, is significantly harder.
Requires deeper understanding, long-term consequences.
Absolutely. It requires the AI to develop a deep understanding of long-term consequences despite partial information. And within this challenging, confounded POMDP setting, the paper identifies two critical, less investigated issues that most existing methods simply haven't adequately addressed. Big gaps.
Okay, what are they?
The first one is continuous action spaces.
Right, you mentioned that earlier. Why is that such a hurdle, and why haven't other approaches tackled it effectively?
Well, many real-world decisions are inherently continuous, not discrete. Think about the steering angle of a self-driving car. It can be any tiny increment within a range, right?
Yeah, not just left, right, straight.
Exactly. Or the precise drug dosage a doctor prescribes, which can be titrated up or down. It's not just option A, B, or C. It's an infinite spectrum of possibilities. Existing offline RL methods, particularly those trying to deal with unmeasured confounders, have largely focused on discrete actions because, well, they are simpler to model and optimize.
So they simplify the problem.
They simplify it. A common workaround for continuous actions is to discretize them, basically, turning that smooth range into a finite series of distinct points, like deciding to steer at exactly 10 degrees, then 20, then 30, and nothing in between.
And I imagine that comes with its own set of problems, like a lose-lose situation.
You've hit the nail on the head. As noted by pioneering research back in 2015, simple discretization introduces significant bias if you use a coarse grid, meaning too few points.
Yeah.
You lose the crucial nuance.
The fine control.
The fine control, leading to suboptimal decisions because the AI can't select the precise optimal value. On the other hand, if you try to use a fine grid with many, many points to capture that nuance, you run headfirst into the infamous curse of dimensionality.
Too many options.
The number of possible discrete actions explodes, making the problem computationally intractable, often impossible to solve within reasonable time or memory. So it's catch-22. Too coarse, you lose accuracy. Too fine, it's impossible to compute. This paper bravely dives into this challenge directly.
Okay, that's a big one. And the second issue they tackle is the critical distinction between policy optimization versus mere policy evaluation. Why is that so important? I mean, evaluating a policy seems pretty useful already.
It is useful, definitely, but it's only half the battle. Much of the prior research in these confounded settings has focused almost exclusively on evaluating a given policy's value. So if I tell you exactly what the AI will do in every situation, you can estimate how well it would perform.
Like grading its homework.
Kind of, yeah.
Yeah.
That's valuable for understanding existing systems. But the real challenge, and what's absolutely paramount in fields like personalized medicine or robotics, is not just knowing if a strategy is okay, but actively learning the optimal policy from batch data. It's about active improvement and discovery, not just assessment.
Finding the best way.
Finding the best possible treatment strategy, the most efficient path. While some previous efforts have touched upon optimization, they often applied to simpler contextual bandit settings or finite horizon problems, or relied on very restrictive assumptions that just don't hold in these complex infinite horizon POMDPs. Developing computationally viable, robust policy learning algorithms for these settings has remained a significant open challenge, until now, arguably.
Okay, that meticulously sets the stage. So the paper truly aims to bridge these two major gaps, handling continuous actions and actively learning optimal policies, even with these unmeasured confounders. They frame their overall contribution as threefold. Can you give us a tantalizing glimpse of what revolutionary solutions they propose?
Indeed. They tackle these formidable challenges head-on with remarkable ingenuity. Their first main contribution is a novel identification result for off-policy evaluation. This allows them to precisely determine the true value of a policy even with continuous actions and, crucially, those elusive, unobserved confounders.
Okay, so accurately measuring performance.
Right. Second, building on that, they introduce a brand new policy gradient algorithm specifically engineered for the monumental task of learning the optimal policy under these incredibly difficult conditions.
Actually finding the best strategy.
Exactly. And third, to bolster the confidence in their breakthroughs, they provide robust theoretical guarantees that rigorously back up the reliability and performance of their proposed methods, ensuring they're not just clever heuristics but mathematically sound solutions.
That sounds like a comprehensive and elegant stack of solutions. So let's peel back the layers and move into part two. Seeing the unseen, a novel framework for confounded POMDPs. Where do they even begin to construct a framework that can see what's hidden? How do you start tackling that?
Well, their foundational approach is to extend what's known as the proximal causal inference framework to this infinite horizon POMDP setting. This framework, originally developed for simpler causal problems in statistics, is designed precisely to help identify true causal effects even when unmeasured confounders are present. It's about finding indirect ways to account for those hidden influences.
Proximal causal inference. Okay. And the absolute key innovation here, the linchpin, is something they call reward-inducing proxy variables, or W3. This sounds like a bit of a magic bullet. What exactly are these W3 variables, and how do they help pull back the curtain on the unobserved?
They are incredibly clever. These Willity variables are ingeniously selected auxiliary variables that provide a crucial bridge, a kind of indirect sensor to the unobserved information. They're specifically defined as variables that relate to the action only through the full state that's both the observed O and the unobserved S components, and critically, are unaffected by the action itself.
Unaffected by the action.
Interesting.
Think of them as passive observers that pick up on the hidden dynamics of the system without being directly influenced by what the AI agent does. They're essentially indirect windows into the parts of the state we can't directly measure.
That's a really counterintuitive idea. Can you give us some concrete examples of these Woody-T variables from the paper? How do they manifest in real-world scenarios? Certainly. The paper offers several excellent relatable examples. In a general sense, a WARD could be environmental factors that are clearly correlated with an outcome, say the reward RT, but are provably not directly affected by the action at.
Yeah.
For instance, in healthcare, WARD might include the specific choice of doctors or hospitals administering a treatment. These choices can influence patient outcomes, certainly, but the AI's decision on the drug dosage doesn't directly change which hospital the patient goes to, right?
Oh, right. That's determined by other factors.
Exactly. Or they could be variables that only become available after the treatment, such as detailed patient adherence data. Did the patient actually take their medication as prescribed? This clearly influences the outcome, but it doesn't influence the doctor's initial choice of treatment, given the full picture available at that moment. This independence from the action is what makes water such a powerful, untainted lens into the unobserved.
That's a very clever way to frame it. And they also mentioned the German family panel, the PairFam study, as a real-world example. How do they identify weedy variables in the context of something as messy as human relationships?
Yeah, the PairFam example is particularly fascinating because it applies this highly technical framework to something so profoundly human. In the PairFam study, the weedy variables could be things like housing conditions, household income, the division of labor within the household, or even the mere presence of relatives during an interview.
Things that provide context but aren't the direct action.
Precisely. These variables undoubtedly influence overall relationship satisfaction, which is the reward in this context, but they are not directly decided by intimacy frequency, which is the action, how often partners share feelings. These witty elements provide a context that shapes the relationship's underlying health without being a direct consequence of whether a couple chooses to open up or not at a given moment. It fits the definition perfectly and really highlights the versatility of this framework.
I remember seeing a diagram, a directed acyclic graph, or DDAG, in the paper that visually represents these causal links. How does it illustrate the crucial role of WT? Can you maybe describe that visual?
Yeah, the day, specifically the left panel in Figure 1 of the paper, is a powerful visual explanation. It shows how the unobserved states, observed states, actions, rewards, and these new proxy variables all interact within the system. What's truly significant is how wet connects to sign-on, but conspicuously has no direct arrow originating from at.
Ah, showing that independence visually.
Exactly. This visually represents the core assumption that ON is not directly affected by the action. This graphical representation clearly differentiates their model from the classical POMDP depicted in the right panel, which lacks WAD entirely. It highlights the added layer of realism and complexity their framework is designed to capture, essentially making the invisible visible through these carefully chosen indirect pathways.
Okay, so these proxy variables are absolutely central to unlocking the hidden information. But for any statistical model, assumptions are necessary. They're the foundational planks upon which the entire edifice rests. Can you walk us through the technical backbone, the key assumptions, and, more importantly, why each one is critical for enabling the model to see the unobserved?
You're absolutely right. Assumptions are non-negotiable for theoretical guarantees. The first is Assumption 1, Markovian. This is pretty standard in reinforcement learning. It states that future states and observations depend only on the current full state, observed state, and action, not on the entire past history.
The present summarizes the relevant past.
Essentially, yes. It simplifies the problem by assuming that the present contains all the necessary information from the past to predict the future. It's a fundamental property of Markov processes.
Okay, standard stuff. And then there's assumption 2, reward proxy. This one feels like the central nervous system for data.
It is indeed the linchpin. It requires that the reward proxy wit relates to the unobserved state sent when conditioned on the observed state ought, but not to the action at when conditioned on the full current state, which includes both sent and ought.
So what tells you something about the hidden state sent, but isn't caused by the action at?
Exactly. This is what ensures wit provides valuable, untainted information about sent without being a direct consequence of the action taken. It's crucial because it prevents spurious correlations that would mislead the AI. It's also notable, as you saw in the DAG, this assumption doesn't require a direct causal link between wit and the reward art. It acts more like an indirect, instrumental variable.
Got it. And assumption 3, action proxy, what's that about?
This assumption dictates that the previous observed state and action pair, let's call it OTT at 1, does not influence the reward proxy at PRUT or the reward R, given the current full state in action. This ensures that past actions don't create misleading associations through the proxies or rewards when the current context is fully known. These first 3 assumptions are directly verifiable from the causal structure represented in their DAG, which is a powerful way to visually confirm their validity if you believe the DAG structure.
Okay, but the paper notes we still can't directly identify the value of the target policy with just those. That's where assumption 4, completeness, comes in, which they describe as the most complex but vital. This sounds like the secret sauce for how they get around the unobserved state. How does this mathematical magic trick work?
Assumption 4, often called completeness, is indeed the truly profound one, the one that truly allows them to see through the fog of the unobserved state. Think of it like this. Even if you can't see sent, the truly hidden part of the puzzle, this assumption essentially states that the history of what you could observe and what actions were taken in the immediate past.
So, OI1 and at1.
Exactly. OI1 at 1 contains just enough subtle clues, enough echoes to infer what sent must have been doing, or at least its relevant aspects.
So it's almost like knowing a person's recent observable behavior allows you to make a pretty good guess about their hidden intentions, even if you can't read their mind directly.
That's a great analogy. Part A of the assumption essentially says that the previous state-action pair, OA1 at 1, must contain sufficient information from the unobserved state sent when conditioned on the current observed state and action. It prevents a scenario where sent is completely disconnected with no echoes in the observable past.
Okay, so the past holds clues.
Right. Then Part B ensures what's called the injectivity of the conditional expectation operator. This is a bit of a mathematical deep dive on its own, but at its heart, it's about preventing ambiguity. It essentially says that if 2 different hidden stories or conditions appear to lead to the exact same average outcome when we look at the observed data conditioned on the past, then those hidden stories must actually be the same in a relevant sense.
No 2 different hidden causes producing the exact same observable effect pattern.
Precisely. It's a way of ensuring that despite the hidden variables, our model can still draw accurate conclusions about cause and effect by leveraging the observed history. Without this completeness in the historical data, the unobserved would remain forever out of reach, mathematically speaking. It's a common yet powerful assumption in advanced causal inference, akin to what's required for instrumental variable identification in econometrics.
That's incredibly intricate, really making something profoundly hidden indirectly inferable through careful mathematical reasoning. Building on these sophisticated assumptions, the paper introduces what they call Q-bridge and V-bridge functions. What are these bridges conceptually, and why are they so pivotal to identifying the true policy value?
These bridge functions are key theoretical constructs that allow the true policy value to be identified even with unobserved states. The Q-bridge function, let's call it QPOT, what it at, essentially represents the expected long-term discounted sum of rewards given the current observed state ought, the current proxy variable WT, and the current action at. Crucially, it implicitly accounts for the unobserved state that influences this outcome through the structure imposed by the assumptions and the use of what.
Okay, so it's like a value function but incorporating the proxy.
Exactly. And similarly, the v-bridge function, vest-tor, represents the expected long-term discounted sum of rewards given just the observed state oat, and the proxy variable wa, again, implicitly accounting for the hidden state oat after averaging over the actions taken by the policy. They act as bridges that connect the observable world, OWA, to the full hidden reality involving S, allowing us to quantify the value of a policy despite the missing information.
So they're like specialized value functions that have learned to incorporate the subtle clues provided by the proxy variables and the past. And the paper notes that while these specific bridges aren't necessarily unique, the policy value they ultimately help identify is unique. How can that be? If the bridge isn't unique, how can the destination be?
That's a profound point, and it speaks to the robustness of the identification strategy. While there might be multiple mathematical functions that could serve as valid Q bridges or V bridges, satisfying all the underlying equations and causal assumptions, the ultimate quantity we care about, the overall value of the policy you're trying to estimate, its true long-term performance will be consistently and uniquely identified, regardless of which valid bridge function you happen to find or use in the calculation.
So different paths up the mountain lead to the same summit value.
Exactly. They all converge on the same true policy value. This consistency is absolutely vital for the reliability of the method. It means the final answer doesn't depend on some arbitrary choice made during the intermediate steps.
Okay, now here's where it gets really interesting, as you said. The identification breakthrough, theorem 3.1. This sounds like the moment they finally connect all these dots. What does this theorem establish, and how does it fundamentally change our ability to work with unmeasured confounders?
This is truly the heart of their theoretical contribution, the moment of revelation, if you will. Theorem 3.1 formally establishes that, under their carefully crafted set of assumptions, 1 through 4, these Q bridges and V bridges always exist.
So the things they need actually exist mathematically.
Yes, this isn't a minor point. It means their entire theoretical framework is sound, and the quantities they're trying to estimate are well-defined and discoverable. Crucially, from this existence proof, they derive a groundbreaking identification equation, equation 3.3 in the paper. This equation is the core mechanism, a mathematical identity.
What does it say in essence?
In essence, it reveals how the difference between the immediate reward, the Q bridge at the current step, and the V bridge at the next step, when all are meticulously conditioned on the previous state action pair, OT1 at 1, and the current observed state in action, must equal 0 in expectation over the randomness induced by what?
Whoa, okay, that's a lot of conditioning. So the mathematical key here is that by leveraging and conditioning on that previous state action pair, OT1 at 1, they find a way to address the issue of the unobserved state saint, effectively allowing them to unlock that hidden information, even though saint itself remains unseen. It's like finding the shadow of a hidden object based on where the light was previously.
Precisely. That's an excellent analogy. By skillfully leveraging the information embedded in the previous observed action and state, the faint echoes of the hidden state saint, thanks to assumption 4, they create a mathematical pathway to implicitly account for saint. This identification equation forms the mathematical basis for how they can then robustly estimate these bridge functions from purely offline data, and ultimately determine the true value of any given policy. It's a truly ingenious way to infer the unseen by carefully analyzing its ripple effects on the observable past and the proxies.
Moving from this elegant theory to practical application, how do they actually use this identification equation to build something concrete, like a minimax estimator, for these bridge functions from pre-collected data? What does minimax mean in this context, and why is it important for robustness?
Right. Theory is great, but you need an algorithm. The identification equation, which essentially states that a certain conditional expectation should be 0, lends itself perfectly to a minimax estimation approach. They define a loss function, let's call it LQF, which captures this expectation using the candidate Q bridge Q and a critic function F. Then they formulate the problem as finding a Q, their estimate of the Q bridge, that minimizes the worst-case error over all possible valid critic functions F. This process yields the minimax estimator, Q.
Okay, minimizing the maximum error. Why that approach?
The minimax part means it's designed to be exceptionally robust. It minimizes the maximum possible error that could occur due to uncertainty or variations in the underlying data distribution or model specification. This makes the estimator far less sensitive to minor inaccuracies or unexpected noise in the real-world data compared to, say, just minimizing average error. It's essentially a strategy that prepares for the worst-case scenario, leading to more reliable and trustworthy estimates, which is crucial when dealing with hidden confounders.
And they propose a computationally efficient fitted queue evaluation, FQE type algorithm 1, to actually implement this estimation of the policy value. How does that algorithm work in practice?
That's right. Algorithm 1 outlines a practical, iterative process, often based on stochastic gradient descent, SGD, to estimate the parameters of the Q-bridge function, represented by Q. It iteratively updates these parameters by computing stochastic gradients derived from that minimax loss function, LUF, using batches of data. This makes it feasible to implement even with large data sets. It's a clever way to incrementally refine the estimates of these bridge functions without having to solve the entire complex minimax problem perfectly at once.
What's truly fascinating here, though, is how they manage the complexities of that minimax problem itself. It sounds like those are typically quite difficult to solve, often tripping up even seasoned researchers. How on earth did they manage to make this computationally feasible? Did they find a clever shortcut, or is it a brute force triumph?
This is where the researchers pulled a genuinely clever trick, a really nice piece of theoretical engineering, to make this work in the real world. Minimax problems, especially infinite-dimensional ones like this, are notoriously difficult. They often require complex, nested optimizations optimizing Q while simultaneously finding the worst-case F, which can be computationally prohibitive and unstable.
Right, sounds nasty.
But they found a way to reframe that incredibly complex minimax problem into something far more manageable. They show that if you represent the critic function, f, within a specific type of function space called a reproducing kernel Hilbert space, or RKHS.
Okay, reproducing kernel Hilbert space. Quite a mouthful. Can you give us an analogy for what that means and why choosing that space is such a game changer for this problem?
Think of it like untangling a Gordian knot. Instead of hacking through it with brute force, they found a specific mathematical lens, this special space defined by a kernel function, that essentially provides enough structure to allow the knot to be untied elegantly. An RKHS, conceptually, is a space of functions where evaluating the function or measuring similarity between functions can be done efficiently using a kernel function. By restricting the critic function f to live within an appropriate RKHS, they leveraged the mathematical properties of these spaces.
And what does that structure do for the minimax problem?
It allows them to decouple the complex minimax problem. They show, remarkably, in Theorem 3.3 and 3.4, that the inner maximization over f, finding the worst-case critic, has a closed-form solution or can be easily computed within the RKHS framework. This transforms the difficult two-player game, min-max, into a much simpler single-stage minimization problem just over the parameters of the Q-bridge queue.
Wow, so choosing the right mathematical playground simplifies the game dramatically.
Exactly. It's a crucial technical detail that makes the entire method practical and computationally tractable, avoiding the instability and prohibitive costs that often plague direct solutions to minimax optimization. It transforms theoretical elegance into something you can actually code and run.
That's an incredible leap in making it applicable. Now let's transition into part 3, the quest for optimal action policy learning. We've talked about estimating the value of a given policy, which is a powerful diagnostic tool. But as we discussed, the real power, the ultimate goal, comes from learning the best possible policy or any way. How do they go about achieving this ultimate goal, especially given all these underlying complexities?
Right. Evaluation is step one. Optimization is the goal. Since directly optimizing the optimal policy itself can be intractable, especially in high-dimensional continuous action spaces with hidden confounders, searching through all possible functions is impossible.
Yeah, infinite possibilities.
So the solution they propose is standard but effective here. Parameterize the policy distribution. This means they don't try to find the policy directly in that infinite function space. Instead, they represent the policy using a finite set of adjustable parameters. Let's call them zeta. Think of these parameters as knobs on a machine that controls the AI's behavior.
Okay.
By iteratively adjusting these parameters, the algorithm can effectively learn the optimal policy by searching within this more manageable parameter space, zeroing in on the best set of instructions, the best knob settings for the AI.
So instead of trying to find the perfect policy from an infinite space, they find the best parameters for a predefined but flexible policy structure that makes it a tractable search problem.
Exactly, and this offers a great deal of flexibility. These policy parameters that can be modeled using simpler, more interpretable linear basis functions. Maybe the policy is just a weighted combination of observed features, or they can leverage the immense power and expressive capacity of complex neural networks to represent much more nuanced policies.
Giving you a trade-off.
Right. The choice allows for a strategic trade-off between interpretability, understanding why the AI makes a decision, and sheer modeling capacity, adapting to the specific needs and inherent complexity of the problem at hand.
They then describe an iterative dance, their policy gradient algorithm, algorithm 2. Can you walk us through that two-step process? It sounds like a sophisticated feedback loop.
It's an elegant and powerful iterative approach, very common in RL, but adapted here for the confounded setting. In the first step, given the current set of policy parameters, they precisely estimate the Q-bridge function, Q, using their minimax estimator from algorithm 1. This provides an accurate estimate of the value of taking different actions under the current policy PO, even with unmeasured confounders.
So step 1, figure out how good the current strategy is, accurately.
Right. It's essentially the AI evaluating its current decision-making strategy using that robust Q-bridge estimate. Then, in the second step, they calculate the policy gradient, which we can denote as DEB, based on this accurately estimated Q-bridge. This gradient is essentially a directional arrow, a vector that tells the algorithm exactly how to adjust the parameters to improve the policy's expected long-term value.
It points uphill towards better performance.
Exactly. It points in the direction of steepest ascent in the policy value landscape.
And they use gradient ascent to update DEB repeatedly until convergence.
That's right. Gradient ascent is the mechanism used to update DEB, moving the policy parameters incrementally in the direction indicated by the gradient, nudging the policy towards better decisions that yield higher estimated long-term rewards. This two-step process, first accurately evaluating the current policy's value using the Q-bridge, and then updating the policy parameters based on that evaluation's gradient, repeats iteratively.
Until it settles.
Until convergence is attained, hopefully near a local optimum. At that point, the algorithm has approximated the optimal policy within the parameterized class and its corresponding Q-bridge, meaning it has learned the best possible strategy you can find given the data, the parameterization, and the presence of hidden factors.
This iterative process, especially with continuous action spaces, raises an important question. How does this method make it computationally feasible? Because typically, optimizing over continuous actions can bring computation to a grinding halt. What's the advantage here?
That's a crucial point, and it's one of their core computational advantages compared to some alternative policy iteration approaches. This policy gradient method cleverly avoids a common bottleneck. Many traditional policy iteration algorithms, particularly with continuous action spaces, would often require solving an additional complex optimization problem within each iteration. Explicitly finding the action A that maximizes the current Q function, max QOWA.
Searching the entire continuous action space for the peak value.
Exactly. That maximization step can be incredibly demanding and often intractable in continuous spaces. By formulating it as a policy gradient method that estimates the Q-bridge and then calculates gradients with respect to the policy parameters of their proposed method offers significant computational advantages. It doesn't need to solve that difficult, explicit maxa optimization problem directly at every iteration. It learns by iteratively adjusting the policy parameters of in the direction of higher value, which is often a much more efficient process, especially when using automatic differentiation tools with neural networks.
That's a huge practical benefit, transforming a theoretical possibility into something that can actually run on a computer in reasonable time.
Now, for part 4, the proof is in the pudding, theoretical guarantees and simulations. In AI research, it's one thing to propose an algorithm, but you need rigorous theoretical foundations to trust its reliability, especially for high-stakes applications. What kind of ironclad guarantees did they provide for this whole framework? Theoretical results are absolutely crucial. They provide the bedrock of trust. The authors provide several key guarantees that instill confidence. First, consistency. They prove, Theorem 4.1, that their estimator for the Q-bridge, Q, consistently converges to the true Q-bridge as more data, and the number of trajectories, is collected.
Meaning it gets closer and closer to the truth with more data.
Precisely. Think of this not as a dry academic proof, but as the foundation of trust. It's their promise that, given enough data, their algorithm will eventually converge on the true value of a policy, accurately accounting for those hidden influences. In fields like medicine or autonomous driving, that's not just a nice to have. It's the difference between a reliable system and a dangerous gamble. It's the getting it right eventually guarantee.
And what about how fast it gets it right? Do they provide finite sample error bounds, telling us the rate of convergence? That's important for knowing how much data you actually need.
Yes, they do, which is incredibly important for practical deployment. This is captured in Theorem 4.2. They show that the error in the estimated policy value converges at an optimal statistical rate of ON12.
Okay, 1 over root n. That's pretty standard and good, right?
Yes, it's considered the optimal rate for many parametric estimation problems. It means that the accuracy of their estimate improves relatively quickly as you increase the amount of data in. It provides quantifiable confidence in the estimation. You know roughly how much data you need to achieve a certain level of accuracy. It tells us that with just a reasonable amount of data, you can expect a good, reliable estimate, and doubling the data will reduce the error by a predictable factor.
And finally, regret bounds. What does that tell us about the quality of the learned policy compared to the absolute best possible one? This seems key for the optimization part.
Regret bounds are critical for policy learning algorithms, measuring how close the learned policy gets to the true optimum. Theorem 4.3 demonstrates that the difference between the true optimal policy value within their chosen policy class and the value of the estimated optimal policy also converges. Specifically, it converges at an optimal minimax rate of OP12N12.
Okay, so it depends on P, the number of policy parameters, and N, the amount of data.
Exactly. P represents the complexity of the policy class. This result means their learned policy not only converges towards the best policy in its class, but it does so at a theoretically optimal speed, balancing policy complexity and data availability. It quantifies how quickly their algorithm minimizes the performance gap between what they learned and the true best possible policy within that class. This is powerful assurance that the algorithm isn't just making random improvements, but efficiently zeroing in on the best strategy it can represent.
To make these robust guarantees possible, they must rely on some critical assumptions beyond the standard ones about the policy class, like smoothness, compactness, and reward function, boundedness. What's a particularly vital assumption for success here? One that often dictates the real-world applicability of offline RL.
The most vital one for the applicability of any offline RL method, and this one is no exception, is assumption 10, coverage. This assumption essentially states two things. First, the collected offline data must sufficiently cover the entire state action space that the policy we want to learn might visit.
The data has to explore enough.
Right. Think about it. If your dataset only shows one type of behavior, or if certain crucial states or actions are never recorded, say, a self-driving car only ever sees sunny highway driving and never icy city streets, it becomes incredibly difficult, maybe impossible, for the algorithm to learn how to act optimally in those unobserved scenarios. You simply can't reliably learn what's not in your data.
Makes sense. And the second part?
The second part is that the target policy you want to learn must be absolutely continuous with respect to the behavior policy that generated the data. This basically means that any action the target policy might want to take in a given state must have had some probability, even if small, of being taken by the behavior policy in that state in the collected data.
So the data has to have at least some examples relevant to the policy you're trying to learn.
Precisely. It prevents the algorithm from trying to evaluate or learn actions that were literally never seen in the historical data for certain situations. Without sufficient coverage, the theoretical guarantees can't hold because the algorithm might be forced to extrapolate far beyond what it's ever seen, which is a recipe for disaster in critical applications. This is a major practical challenge for all offline RL.
Okay, so the theory is sound and rigorous, but relies on this crucial coverage assumption. How do they demonstrate this in practice? They had to conduct extensive simulation studies, right? Since their problem framework is so novel, continuous actions plus proxies, what do they compare their method against?
Precisely. Empirical validation is key. Since no existing methods directly fit their complex framework, they had to compare their proposed method against a set of carefully chosen baselines that represent the closest existing approaches or natural simplifications. For policy evaluation, they compared against 1. MDP baselines, basically ignoring the confounders and pretending the observed state O is the true state S. 2. Augmented MDP, MDPW, a slightly smarter baseline that treats the combined observed state O plus proxy variable W as the new state, still potentially incomplete, but maybe better than just O.
Trying to use the proxy, but in a simpler MDP framework.
Exactly. And for policy learning, they benchmarked against state-of-the-art deep RL methods commonly used in standard MDP settings like IQL, SAC, and CQL. These methods are powerful but aren't explicitly designed for unmeasured confounders addressed via proxies.
They used a synthetic environment for testing. Can you describe that briefly? What did it allow them to control, and what were the key takeaways from their simulation results, or particularly for policy evaluation? What did it really prove?
The synthetic environment they created was a meticulously designed setup. It had a one-dimensional continuous state space and a continuous action space, making it challenging but controllable. They precisely defined the mathematical equations governing the reward, state transition, and crucially, the generation of the unobserved state and the proxy variable. This allowed them to know the ground truth and control the strength of the confounding.
So they knew the right answer beforehand.
Exactly. It allowed them to evaluate exactly how well their method recovered the true underlying dynamics when those confounders were present. They also deliberately designed the behavior policy that generated the data to ensure sufficient coverage, satisfying assumption 10, so they could focus purely on the confounder challenge itself. In terms of policy evaluation, vividly depicted in Figure 2 of their paper, the results were strikingly clear. Their proposed method, the one using the proximal framework and identification theorem, consistently showed significantly lower bias in estimating policy value across all sample sizes. It was much closer to the true value.
So what does this all mean for someone trying to deploy AI in the real world? It sounds like it confirms their theoretical claims about seeing the unseen via proxies.
Exactly. It provides the empirical validation that leveraging their novel identification result by effectively using those reward-inducing proxies, YDPs, successfully recovers lost information from unobserved variables. This is the core proof of concept, that you can effectively deal with hidden factors using this approach.
And the simpler methods.
In stark contrast, the simpler MDP and MDPW methods exhibited substantially higher bias and variance. This is because they either completely ignored the unmeasured confounders, MDP, or in the case of MDPW, imperfectly addressed them by treating a potentially noisy combination of observations and proxies as the true state. They simply couldn't account for the full picture, leading to wildly biased and unreliable estimates of how good a policy truly was. It's the difference between navigating with a clear map versus a blurry, incomplete sketch.
That's a powerful validation for the accuracy side. What about the policy learning simulations shown in Table 1? How did their method fare there in actually finding the optimal policy to learn better strategies?
Yes, for policy learning, their proposed method consistently outperformed all competing approaches across varying sample sizes in terms of the final value of the learned policy. And it did so while remarkably maintaining comparable variance, meaning it wasn't just getting lucky sometimes.
And why did it do better? What's the mechanism?
This advantage stems directly from its ability to achieve unbiased estimation of policy value at each iteration via the Q-bridge estimator. This unbiased evaluation of how good is my current strategy leads to accurate policy gradients. Accurate gradients ensure that the policy parameters are updated in the correct direction, truly moving towards optimality rather than being led astray by hidden influences biasing the value estimates.
And the standard RL methods.
Methods designed for pure MDP settings like IQL, SAC, and CQL performed significantly worse when unmeasured confounders were present and strong. This powerfully underscores the importance and necessity of this new framework for real-world scenarios where unseen factors are inevitable. They just weren't equipped to handle the confounding.
And it showed stable performance even with relatively small sample sizes. That's quite desirable in many applications where data is a precious commodity, where you don't have millions of data points to play with.
Absolutely. Think about medical data for rare conditions. You don't have millions of patient trajectories. Or data from complex, expensive industrial processes. The ability of this method to perform well, even with limited data, makes it highly practical and potentially deployable in precisely those high-value, data-scarce domains. It means you don't necessarily need a perfectly boundless data set to start deriving powerful insights and better policies.
They also compared neural networks versus simpler linear models for parameterizing the policy. What did they find regarding that trade-off between the raw power of neural networks and the interpretability of linear models?
Neural networks, as you might expect, often showed superior performance in the simulations due to their richer function class. Their inherent complexity allows them to learn more intricate and potentially closer to optimal policies, especially if the true optimal policy is highly nonlinear. However, and this is a significant finding with profound practical implications, they also highlighted that linear policy classes achieved comparable performance in many of their simulation settings.
So you get similar results, potentially, but with fewer and crucially more interpretable parameters. That's a critical practical trade-off, isn't it? Especially if you need to explain why an AI is making a certain recommendation to a human expert, like a doctor or a policymaker. The black box problem is a big one for adoption.
Precisely. In many real-world applications, particularly in fields like medicine, social science, or even financial regulation, interpretability isn't just a bonus. It's often paramount for trust, validation, and accountability. A linear model provides clearer, more transparent insights into which observed variables are driving the optimal action, A equals O, making it much easier for human experts to understand, validate, and crucially trust the AI's recommendations. It bridges the gap between algorithmic sophistication and human understanding, a key challenge in AI adoption. This finding suggests you might not always need the full complexity of a neural network.
Now, for perhaps the most intriguing part of our deep dive, let's transition to part 5, real-world impact optimizing relationships with AI. This is where the rubber truly meets the road, and they apply their sophisticated method to a fascinating and deeply human dataset. The German family panel, or PARFAM study. Can you tell us about PARFAM and why it's a near-perfect fit for a confounded POMDP?
The PARFAM dataset is truly unique and rich. It's a comprehensive longitudinal dataset that has been meticulously tracking romantic relationships and family structures in Germany since 2008, encompassing an impressive 14 waves of survey results from thousands of individuals over many years.
Wow, that's a lot of data on relationships.
It provides an unparalleled, long-term view of the intricate dynamics of how human relationships evolve. The reason it's such a perfect fit for a confounded POMDP is profoundly insightful. The true feelings, underlying emotional states, the deep-seated compatibility, and private thoughts of participants regarding their relationships are inherently unobserved.
You can't directly measure someone's true feelings.
Exactly. These are akin to the hidden state in our model. Survey responses, while valuable and indicative, are merely proxies or noisy observations for these deeper underlying sentiments and states. This perfectly mirrors the core challenge. Crucial influencing factors are not directly visible to the model, making relationship dynamics an ideal, complex, real-world, confounded POMDP problem.
And the objective here was to estimate the optimal strategy to maximize long-term relationship satisfaction using this data. This sounds incredibly ambitious. How do they translate those abstract RL concepts reward, action, observed state, and those clever reward proxy variables into concrete real-world relationship terms that the AI could actually work with?
They meticulously mapped each component, which is always a critical step in applying these methods. The reward was defined quite naturally as the mean relationship satisfaction reported by the couple during each survey wave, a direct measure of the desired outcome.
That makes sense. And the action?
For the action, which crucially needed to be continuous to leverage their method's strength, they selected the frequency of sharing private feelings and communicating with partners, aptly referred to as intimacy frequency. This is treated as a continuous variable based on survey responses, allowing for a nuanced range of actions from very little sharing to very frequent sharing.
Okay, so sharing more or sharing less is the continuous action. And what about the observed state and the proxies? How did they identify which aspects of a relationship could be observed versus those that served as proxies for the hidden stuff?
The observed state was constructed as a 6-dimensional vector, including measurable aspects reported in the surveys like the frequency of conflicts within the couple, the frequency of showing appreciation, each partner's general health status, the couple's future orientation that they plan together, their reported sexual satisfaction, and their satisfaction with the friendship aspect of their relationship. These are all things that can be somewhat reliably observed or reported directly.
Okay, tangible aspects. And the proxies. What served as those indirect windows?
For the reward proxy, the WT, they used a 4-dimensional vector comprising housing condition, for example, type, size, household income, the reported division of labor between the couple, and interestingly, the presence of relatives during the interview. The key here, as they argue based on existing relationship literature, is that these variables are considered plausibly independent of the intimacy frequency action when conditioning on the observed states.
So your income doesn't directly change just because you shared your feelings more this week, assuming we account for conflict levels, etc.
Right. These factors likely influence the underlying relationship health, or maybe even how satisfaction is reported, the reward, perhaps reflecting underlying stress or support systems, part of the hidden state and stay, but they are not directly changed by the couple's specific action of sharing feelings in that moment. They provide that critical, indirect window into the unobserved context satisfying assumption too.
That's a truly thoughtful and well-reasoned mapping of abstract AI concepts to messy human behavior. And they started with a pretty substantial data set too, after careful data cleaning, right? 809 trajectories over 14 time points?
Yes, it's a robust data set for this kind of intricate longitudinal analysis. They ensured data quality by meticulously handling missing values, which is crucial for the reliability of any machine learning model applied to real survey data. This robust data set allowed their framework to learn meaningful patterns.
So once they had their data meticulously prepared, they applied their method using both neural nets and linear policies. What did they find was the optimal relationship strategy? I'm particularly interested in the insights derived from the linear policy given its interpretability, which you highlighted as a key advantage.
Right, so they applied both policy classes, just like in their simulations. And consistent with those findings, the linear policy class provided remarkably similar performance in terms of estimated value, but with significantly more interpretability. This allowed them to examine the learned optimal policy in a way that resonated directly with human understanding and existing relationship science.
How did they illustrate it?
To make the linear policy's recommendations concrete, the researchers carefully constructed 4 distinct scenarios based on common couple dynamics. These scenarios were defined by varying levels of commitment, future orientation, and conflict frequency, representing archetypal relationship states. The specific values are in Table 3, normalized for clarity.
Okay, so different types of couples. Can you give us some examples of what the model suggested for these different scenarios? What were the practical takeaways? Did it just say, talk more?
Far from it, actually. For scenario 4, which characterized couples experiencing a high frequency of conflicts and low levels of commitment, essentially, relationships in significant distress. The model suggested that fewer instances of sharing feelings and thoughts, lower intimacy frequency, was the optimal path to improve long-term satisfaction.
Wait, share less in a high-conflict relationship? That seems incredibly counterintuitive to most standard advice.
It does, doesn't it? But it implies that in highly distressed relationships, perhaps too much intense intimate sharing might actually be detrimental. Maybe it overwhelms coping mechanisms, gets misinterpreted, or simply fuels more conflict rather than resolving it. Withholding might, in that specific context, be a protective or stabilizing strategy, at least according to the model trained on this data.
That's a truly surprising and potentially actionable insight. It challenges our assumptions, revealing a deep, almost counterintuitive pattern that withholding can sometimes be adaptive in distressed relationships. What about the other end of the spectrum?
Exactly. In stark contrast, for scenario 3, representing couples with low conflict and high commitment, a healthy, stable relationship, the model preferred more frequent sharing of feelings. This aligns perfectly with common wisdom and research. Openness, emotional intimacy, and frequent communication foster stronger, more satisfying bonds in already healthy relationships.
Okay, that makes more intuitive sense. And the middle ground scenarios.
For scenarios with moderate levels of commitment and conflict, scenario 1, moderately high commitment and conflict, and scenario 2, moderately low commitment and conflict, the model consistently recommended moderate to high levels of sharing, suggesting a nuanced approach where the benefits of sharing likely outweigh the risks in these less extreme situations.
That's absolutely fascinating. If we connect this to the bigger picture, how do these AI-derived insights align with existing relationship literature? Do they actually make sense to human experts, or is it just the AI finding weird correlations?
This is one of the most compelling aspects of the application, the validation against existing science. The AI-derived insights align surprisingly well with the more nuanced findings in relationship literature. While general wisdom often points to the universally positive effects of sharing feelings, self-disclosure, psychological research also shows that withholding feelings can actually be beneficial for individuals with high social anxiety, or in cultures or relationships with a more communal orientation, where individual expression might disrupt group harmony.
So the AI picked up on that nuance.
It seems so. It captured the idea that more communication isn't always the optimal answer, and the context, like conflict level and commitment, really matters. This kind of sophisticated context-dependent insight is something the AI successfully learned from the data, validating its findings against established psychological and sociological research.
And things like partner appreciation, that was something the observed state included, right? Does that fit?
Yes, partner appreciation was in the observed state vector up, and that's also well documented in relationship science. Showing appreciation is known to foster positive interactive dynamics through validation and affirmation, which directly improves relationship satisfaction. So the model isn't just spitting out arbitrary policies based on spurious correlations. It's yielding interpretable insights that resonate deeply with established human understanding. It demonstrates the practical utility of this framework beyond just finding an optimal policy number. It provides a deeper, data-driven understanding of complex human behavior.
Offering concrete strategies for improving something as intangible as relationship well-being. Amazing. We've covered a truly immense amount of ground today, from the deep theory to this very human application. Let's head into our outro. So, just to recap, we've explored a groundbreaking approach to offline reinforcement learning, one that successfully navigates the complexities of continuous actions and, crucially, the persistent presence of those tricky unmeasured confounders.
Yeah, this method offers incredibly robust theoretical guarantees, which are vital for building trust in these systems. And importantly, it has demonstrated superior performance in both extensive controlled simulations and that fascinating real-world application in relationship dynamics. It really showcases its potential versatility across domains, from, autonomous systems to understanding human behavior.
This deep dive really highlights how advanced AI and machine learning techniques can provide actionable insights even when faced with incomplete or hidden information. It's paving the way for more intelligent, more reliable systems in critical fields like healthcare, autonomous vehicles, robotics, and as we just saw, even understanding and potentially optimizing complex human social systems. So looking ahead, what still needs exploring? What are the future horizons for this kind of work? Perhaps, what does the paper not talk about that's still relevant to this exciting frontier?
Well, the paper's authors themselves are quite transparent about several key areas for future improvement and ongoing research. One significant challenge, and one that is often a major hurdle in practice, is data coverage. They assume sufficient coverage for their theoretical results, but in many real-world scenarios, especially with limited data, like in medical applications for rare conditions or maybe unique industrial failures.
The data just isn't there.
Right, this assumption frequently doesn't hold. Addressing how to learn effectively and safely when your historical data doesn't sufficiently cover all possible state action scenarios under the POMDP setting for both policy evaluation and learning remains a critical future research direction. How do you handle extrapolation robustly in this confounded setting? That's a huge challenge.
That makes perfect sense. If your data doesn't adequately cover all possible scenarios, your learned policy will inevitably have blind spots, potentially leading to dangerous decisions in uncharted territory. What about variable selection? In real-world problems, simply deciding which variables to even measure and include as O or WU can be half the battle.
You're absolutely right. In real-world applications, identifying which observed state variables O are most crucial, most informative for formulating the optimal policy, and which variables are good candidates for proxies, the good O that satisfy the assumptions, that's a significant challenge. It's difficult to know definitively if you've included all the important observable factors, or if some are redundant, or worse, if your chosen proxies actually violate the independence assumptions, especially without a ground truth for comparison.
How could AI help there?
Well, systematically studying how AI itself, perhaps through feature selection techniques adapted for this causal setting, can help us better select, prioritize, and understand these key observable and proxy variables would greatly improve the generalization, efficiency, and practical utility of these advanced RL techniques. It's about not just making decisions, but understanding the inputs to those decisions and validating the model structure itself.
And finally, computational efficiency. As these models become more complex, using perhaps deep neural networks for the Q bridge in policy and datasets grow, computation and memory can become major bottlenecks, right?
Yes, absolutely. The proposed algorithm, while powerful and more efficient than some alternatives, can still require substantial computational and memory resources, especially due to the need to estimate a potentially complex Q-bridge function, possibly involving kernel methods or neural nets, and calculate gradients at each policy iteration. Future research will inevitably aim to develop even more computationally and memory-efficient algorithms.
Any ideas how?
Well, a possible direction, though very challenging, might be to try and directly identify the policy gradient under the confounded POMDP structure, perhaps bypassing the explicit estimation of the full Q-bridge function. Finding such a direct and stable method, particularly in continuous action spaces with these proxy variables, remains a formidable challenge for the next wave of research. Making these methods faster and lighter is key for broader adoption.
This work brilliantly shows how AI can learn optimal strategies and unlock powerful insights, even in the face of hidden complexities and incomplete information. To leave you, our listeners, with a provocative thought. Consider what other complex human systems may be the intricate dynamics of organizational management, the feedback loops in urban planning, or the nuanced challenges of public policy design could truly benefit from understanding these hidden influences. Where else are unmeasured confounders driving outcomes, and how could methods like these help us make better, more data-driven decisions for long-term well-being?
It's a powerful reminder that even when we think we see everything, there are often deeper layers silently impacting outcomes. And this research provides a truly powerful framework for beginning to uncover them, paving the way, hopefully, for more informed and effective decisions in many aspects of our lives and society.
That's all for this deep dive. To stay updated on the latest AI and ML research papers, do visit our webpage, which you can find linked in the bio. Join us next time for another exploration into the frontiers of knowledge.